Okay, so over the last few videos, we looked at a strategy for dealing with collisions called linear probing. In this video, we're going to look at the second strategy for dealing with collisions, and it's called chaining. And it's a lot simpler than linear probing. When we use chaining, instead of storing the value directly into the array, each array position contains a linked list. And so for our example, instead of storing the employees or stored employee instances, we would store a linked list. And if we go to add an employee and the key that we use has a hashed value that collides with the hashed value for another key, well, that's okay, because at that position in the array, there's a linked list, and linked lists don't have any boundaries. They're not bounded by size. And so we can just go ahead and add that second employee into the linked list at that array position. So we never have the concept of, oops, sorry, this array position is already filled. And so we don't have to worry about incrementing indices and all that stuff. Now, of course, the drawback is there's a linked list at every position. And so when you go to retrieve or delete an item, you have to search the linked list to find the item with the key you're interested in. But if you have a good hashing function and if you have a good load factor, then these linked lists will typically be short. So let's jump right into the implementation. I've created a new project. I've copied over the code from the last project, some of it. I don't have the last retrieve that we did. I've got our stored employee because this will be what we store in the linked list because we are going to have to search the linked list for the key that we're interested in. I have the usual employee class, and I've created a class called chained hash table, and I've copied over our hashing function because we're going to use the same hashing function. I mean, the hashing function still has to produce an array index. The only difference here is that a linked list will be at that array index. Okay, so we're going to need one field, and that's our hash table. So we're going to say private linked list. We'll just use the linked list class in the JDK, and it's going to be a linked list of stored employee. And we want an array of linked lists, and we'll call it hash table. And so in our constructor, we need to create our hash table. So I'll say public chained hash table. And we'll say hash table equals new linked list, and we want 10 elements. And then we have to initialize each array position with a linked list, an empty linked list. So we're going to say for int I equals 0, I less than hash table.length, I plus plus. And so we're going to say hash table I equals new linked list, stored employee. And that's it. So we create our hash table. It's an array of length 10, except instead of being a stored employee array, it's going to contain linked lists. And then we have to, of course, create an instance of linked list in every position. We could do this on the add method. You know, we could check and see, well, is there a linked list there? But doing it up front just simplifies things. The other way we could potentially implement this, and you might see this if you look at other implementations, is that we create an object array, and then we store either a stored employee if there's only one item, or once we get a collision, we then change that to a linked list. But I think just starting out with linked list is a lot simpler. Okay, so let's go ahead and add the put method. And so we'll say public void put, and we need, as usual, the key value pair. So we'll say string key and employee value. Well, let's just call it employee like we did in the other videos. And the first thing we're going to do, as usual, is hash the key. So we'll say int hash key equals hash key key. And now all we have to do is add the employee to the linked list that's at the position hash key. So we'll say hash table hash key dot add, because there's a linked list at each index, and we'll say new stored employee, and we'll pass the key and then the employee. And that's it. So much simpler. And it doesn't matter here whether we add employees to the beginning or the end of the list, because we have no idea in what order they're going to be retrieved. So it'll be a 6 of one, half a dozen of the other type of thing. And so as you can see, it's much, much simpler. We don't have to worry about, is the position already occupied? And if it is, keep incrementing indices and keep a watch out for traversing the entire array, etc. It's much, much simpler, but it does require more memory because you have the next and previous fields. So let's implement get now. And so we'll say public employee, because we're going to return the employee get, and we need the key. And we'll say int hashed key equals hash key, the key. And now what we need to do is search the linked list at position hashed key for the stored employee that matches this key. And so we're going to use a list iterator to do that. So I'll say list iterator, and it's going to be an iterator of stored employee because that's what we have stored in our lists. Iterator equals hash table hash key dot list iterator. And now we're going to use this iterator to find the employee that has our key. So we'll say stored employee equals null, and then we'll say while iterator dot has next. We'll set the employee to the iterator dot next, and then we'll say if employee dot key dot equals the key we're looking for, then we have found our employee. And so we're just going to return employee dot employee, and we're done. Now, if we drop out of this loop, it means that we've iterated over the entire list and we have not found a stored employee instance that matches the key, and so we're just going to go ahead and return null. And that's our get method. It's quite straightforward, a lot easier to write than using linear probing. So finally, let's add our remove method. So I'll say public employee remove, and we need the key. And I'm going to copy this code here because it's quite similar. So we're going to start out by getting the hashed key. We're going to get the iterator just like we did before, set a stored employee to null, and iterate over the employees. But instead of returning here, we're just going to break. And so when we break out of the loop, there's two possibilities. We have completely traversed the list and we haven't found a stored employee instance that matches, or the stored employee field now contains the employee we're interested in. So we'll say if employee equals null, well, this means that we've traversed the entire list and we didn't find the employee we're looking for. So we'll return null. Else, we did find the employee we're looking for, so we want to remove it from the list. So we'll say hash table, hashed key, dot remove employee. And we'll return the employee dot employee. Remember that this employee local field is actually a stored employee, and we don't need this return null. And that works, and we could probably pull this out and refactor it so that this is in a separate method, but we can improve this remove method, because the way we're doing it now, we're actually going to end up iterating over the list twice, because we're iterating over it here to find the employee that has the key, and then when we call the remove method with the object, the remove method in the linked list class is going to have to iterate over the list again to find this object. Because remember, in a linked list, we've only got, for the JDK linked list, we only have the head and the tail of the list. And we're not asking to remove from the head or the tail, we're saying remove this random employee that you have in the list, and the way that the list has to do that is to traverse the list. Well, we already did that here. And so we're going to change this code to keep track of where we are in the list. And then there's another form of the remove method where we can pass an index. So we can say delete employee 5 in the list. And depending on how the list is implemented in the back end, that can be faster. It may still have to traverse the list, but at least it's not going to have to do all the comparisons again, because with this one, it has to traverse the list. And for every list element, it has to say, is this the employee I'm looking for? Is this the employee I'm looking for, etc. Whereas if we just say remove the guy that's the 5th guy on the list, it may have to move to the 5th guy on the list, but then it can just delete it. And it doesn't have to keep comparing along the way. So it would be faster. So up here, I'm going to say int index equals 0. And then every time we pull something off the iterator, I'll increment that index. And then here we'll say remove, and we're going to pass the index instead. And so that's just a little performance improvement. And because we're doing that here, I won't pull out anything from here because we are needing to do something different in the remove. Okay, and that's it. I mean, that's our remove. Using linked lists makes the implementation easier because there's always room at the hashed location. But that doesn't mean that chaining is better than linear probing. In fact, on average, linear probing performs better than chaining does. It just means that the implementation is a little bit simpler. All right, so one final thing is to implement our print hash table. So we'll say public void print hash table. And what we're going to have to do here is traverse the linked lists at every position. So we're going to say for int I equals 0, I less than hash table dot length, I plus plus, and we'll say if hash table I is empty, I mean, we don't want to traverse an empty linked list, then we'll just system.out.println position plus I plus colon space empty. Now, if the linked list is not empty, then we need to traverse the list. So once again, we'll use a list iterator. So I'll start out by saying position, basically this. Let me just copy this. It'll be faster. Except I'll remove the empty at the end. And then we're going to get a list iterator like we did before. So list iterator stored employee iterator equals hash table I dot list iterator. And then while iterator dot has next, we want to print the employee field in the stored employee. So we'll say system.out. I'm going to change this up here to print. So I'm going to say system.out.print iterator.next.employee. And then we'll print an arrow here, system.out.print. I'll make a single arrow, even though we've learned that the JDK linked list is actually a doubly linked list. And then when we drop out here, I'll do the system.out.println. And I'll say null because the end of each list will point to null. And that's it for our print hash table, and that's it for our implementation. So let's go back to our main method, and now everything compiles. So I guess I never did need Bill. I'll remove him from this file. And so we create a chain hash table, we add 4 employees, and we print the hash table, and then we get Smith, and then we remove Doe and Janes, and we print the hash table again. So let's do this step by step. So I'll comment this out. Let's run. Okay, so here's our hash table. We'll see, as usual, the first 3 positions are empty. John Doe's in position 3. And this time, when we get a collision, we'll see that we have a linked list at position 5. Well, this is a linked list as well, but we have a linked list with more than one employee on it. So at position 5, we have Jane, and then we have Mary. So when we were using linear probing, we kept looking for an empty spot, and Mary got put into position 7. But now there's always room at the hashed value for the key. And so we've added Mary into the list, and we have 2 items at the list, and Mike is at position 6 as usual. So now let's try out our retrieval to make sure that works. So we're going to get Mary. So what's going to happen is we're going to come in and we're going to search this linked list for an employee that was added with the key Smith. And here we go. We got Mary Smith. And finally, let's try to remove some items. And I'll comment out this print hash table so it's not getting in the way. And we're getting an exception. So we'll have to check why that's happening. And it's happening in the remove. So let's go to the remove, and it's happening here. What's happening here is we're getting an out of bounds, and I can see why. It's because the first item on the list is at position 0. The second item is at position 1. The third item is at position 2, etc. But in here, we're coming in and I've initialized index to 0, and then we pull off the first item and we increment the index to 1, when really index should still be 0 because we've only looked at one item. And so when we look at the first item, index should be 0. When we look at the second item, index should be 1, etc. So I'm going to change this to -1 so that when we come in here, we increment to 0. And if we've looked at the entire array and we don't find anything, then the employee will be null. So we're not going to try to remove anything. If the list is empty, employee will be null. So we're not going to try to remove anything. And so that should work okay. So let me pull this down and let's try running again and cross our fingers that we're now not going to get an exception. And we don't. So back in the main method, we removed John Doe, so he's gone from position 3, and we removed Jane Jones, and she's now been taken off the list at position 5, and we just have Mary there. And then finally, let's try to retrieve Mary, because remember, with the linear probing, before we added the code to rehash the table on a remove, once we had removed Jane, we couldn't find Mary. But we won't have the same problem with chaining, so let's add Mary, and let's run. And we can still see Mary. So that's chaining. It's a lot simpler to implement than linear probing, but as I said, that doesn't mean that linear probing is worse than chaining. It just means that you have more code to write. The implementation is a little bit more complex. So what do you think the time complexity of retrieving an item based on a key is when we use chaining? Well, in the worst case, all the instances would have the same hashed value. And so let's say you had this really bad hashing function, and it didn't matter what you gave it, every single key hashed to the value 3. Well, that means that every single item is going to be put into the linked list at position 3. And so when you want to retrieve something, you potentially have to traverse every single item in the hash table. And so the worst case for chaining is linear time when you go to retrieve something. But the key here, no pun intending, is the hashing algorithm. We want a hashing function that will result in the smallest number of collisions. Now, of course, the best case is no collisions at all, but that can be difficult to achieve in practice. But in the average case, let's assume that we have a decent hashing function, then your linked lists aren't going to be that long. And so if we say that k is the average length of a linked list in your hash table, then retrieval will be O of 1 plus k. The 1 corresponds to calculating the hashed value and going to that array position, and the k provides us with an idea of the average length of a linked list. And so whether the time complexity is going to be closer to constant time or linear time will depend on the hashing function and also on the load factor. Now, why does it depend on the load factor in this case? Well, if you're trying to squeeze 100 values into an array of 10, you're going to have a much fuller array in terms of linked lists that are actually having values than if you try to squeeze 100 items into an array of size 50. Because remember, in the hashing function, if we go back to chain hash table, we're always dividing by the hash table.length. So if this gets bigger, your values will be more uniformly distributed. For example, when our array is of length 10, the numbers 5 and 15 are both going to go into position 5. But if we doubled that array to length 20, 5 would go into position 5, but 15 would go into position 15. And if we made that 30 and 40 and 50, then if we were storing higher values, they'd be more evenly distributed. And so as I've said before, and it's important to understand, the hashing function and the load factor are going to be important in determining how well your hash table performs. Anyway, now that we've looked at chaining and linear probing, we can see why having a hashing function that doesn't produce lots of collisions will result in better performance. Okay, so one final note before we go. In our hashing function, we're using the key.length. Now, we could be calling the hashcode method in the string class. And so I'm going to comment this out because this is often how you'll do it. You'll actually call the hashcode method in the class. I didn't do this because I wanted us to focus on the rest of the implementation. But now that we understand and we've seen everything, let's use the strings hashcode method rather than just using the key.length. So I'll say return, and I'm going to say math.absolute value because the hashcode method for string can actually produce negative numbers. And so we have to take the absolute value, and we're going to say key.hashcode. And we're going to mod that by hashtable.length. In a hashing function, you're always going to be modding it by the size of the array because you have to make sure that the values you're returning are valid array indices. And so I'm going to comment out all these guys here that are removing stuff from the hash table, but I will uncomment this print hash table, and let's run again and see how this changes things. And you'll see that our employees are now distributed differently. John Doe and Mike Wilson now hash to a value of 0. Jones hashes to a value of 1, and Smith hashes to a value of 7. Now we're getting collisions here because we have such a tiny array. If we had a larger array, it's possible that we wouldn't be getting any collisions at all. And so that's it for hash tables. In the next video, we're going to take a look at what's available in the JDK. I'll see you there.